All right, so you have probably heard this term before, buffer. What is a buffer? Well, it buffers things. They're actually all over the place and they're extremely important, but they kind of keep pH from changing. How does it do that? All right, so we're going to talk about how it does that, how to calculate pHs with buffers, and how to calculate what happens if you add an acid to a buffer, why that pH doesn't change much, and so on and so forth. Sorry. Okay, so a buffer, definition-wise, it's a solution that contains a weak acid and its conjugate base. That's it. Weak acid, conjugate base. That's it. All right, so weak acid, conjugate base. Why is this important? Well, you have to have an acid part and you have to have a base part, because then they can both neutralize. An acid can neutralize when a base is added, and a base can neutralize when an acid is added. Okay, so they resist change in pH. So you look at this picture over here. I've got, okay, a weak acid, acetic acid, maybe. Oh, that's the example. And a conjugate base. So essentially something that has C2H3O2 minus in it. I add them together. I have a buffer solution. I've got a little bit of everything in there then. I have some of this, the conjugate base. I have some of this, the acid. And then if I were to add sodium hydroxide, or if I were to add hydrofluoric acid, this guy, the base, could neutralize some of the acid, and this guy, the acid, could neutralize some of the base. Okay, so I'm going to show you that. Now, like I said, these are important everywhere, all over the place. You're going to see them in especially if you take like biochemistry or anything having to do with environmental chemistry. There is a buffer in your blood. Your blood has to stay at a specific pH, actually a very specific pH if you want to stay alive. And it needs to stay at about 7.4 pH. So there is an acid and a conjugate base in your blood. Same thing, seawater, which is progressively getting more and more acidic, needs to stay actually kind of basic. It's about 8.2. As it gets more and more acidic, it gets to like 8.1, which you might not think is a big difference, but that is a huge difference when it comes to wildlife. So buffers are extremely important for maintaining pH for life. Okay, so I'm going to show you these buffer reactions. We're going to use acetic acid and the acetate ion because that is my go-to example for a weak acid and its conjugate base. Also because they're used a lot for a weak acid and a conjugate base. So how does it resist this change? What happens when I add a strong base? What happens when I add a strong acid? Why does it buffer? Okay, so essentially, if I add a strong base, that's going to will react with the weak acid. Okay, that's how it gets buffered instead of changing the pH. If I add a strong acid, that will react with the conjugate base part, the base part. And then that will buffer it. That will resist the change in pH. So the reaction that happens if I add a strong base, which is really just OH minus. So if I add OH minus to HC2H3O2, okay, what is going to occur? All right. Well, sorry, that's a C. If you look at this, okay, we're like acid base. What happens? Well, the hydrogen gets transferred, right? So the hydrogen is going to go from here to here. And so I end up with water and C2H3O2 minus, more of that conjugate base. Now, if you look at those products there, do either of those things affect pH? Well, it's water and it's conjugate base. So no, because they don't change the H plus concentration and they don't change the OH minus concentration. So that is how it buffers. There's no more OH minus in there. There's no more H plus in there. So it resists the change of pH. Okay, so what happens when I add a strong acid? So strong acid being H plus. So if I put H plus in, that's going to react with the conjugate base part. So I'm going to be like H plus and C2H3O2 minus. Okay. Hydrogen transfer, that one's pretty easy. It's going to make more of this. Going to make more of that weak acid. Well, HC2H3O2 is not H plus or OH minus, so it doesn't affect pH. So again, this is how it buffers that change in pH. They kind of stick together so that it doesn't affect pH and you don't have all those H pluses floating around. Okay, so how do we calculate the pH for these buffered situations? We actually have a nice, pretty equation for this. It's called the Henderson-Hasselbalch equation. It is one that you will be given. Okay, you do not have to memorize this, though honestly, you're probably going to have it memorized by the time we're done. This is the Henderson-Hasselbalch equation. All you have to have are like, what is the acid? So you need the Ka, and then the concentration of the conjugate base and the weak acid. That's it. Now you can also use this for a Kb. It's just like flipped, or you can calculate Ka and do it. I will give you whatever equation you need in order to do this, so don't worry. Excuse me. So remember, P means negative log of, so this would be the negative log of whatever the Ka is, and that's how you're going to calculate the pH. It is that simple. Now, buffers can't buffer forever. Okay, eventually you're going to run out of weak acid, you're going to run out of conjugate base, and then the pH will change dramatically. This is called the buffering capacity. The buffering capacity is essentially the amount of acid or base a buffer can neutralize. Okay, it is eventually going to run out. The best buffers, or buffers are most effective when your HA concentration, so the weak acid, is the same as your conjugate base concentration. Well, that makes sense, right? If you have the same amount of weak acid and conjugate base, you can essentially buffer the same amount of acid or base. Okay. Now, at this point, when those are equal, if you look at your Henderson-Hasselbalch equation, okay, if I were to plug in HA and A minus and they were equal, well, the log of 1 is 0. So if this is true, okay, if I make a buffer like this, then the pH equals the pKa. All right, so we can actually find the pH of a buffer very easily. If I have the same concentration, it's just the pKa. That's when a buffer is the best. Okay, so we want a buffer in our blood that has a pKa somewhere around 7.4. Okay, and we do, and we kind of change the concentrations a little bit to make it 7.4 according to the Henderson-Hasselbalch equation, but you want it to be around the pKa. That's what makes a best buffer for a specific pH. Okay, so we are going to do some calculations, of course, for buffers when I add a strong acid or a strong base to it. So when it does the buffering or a neutralization. Now you should be thinking, is this going to be an ice table? Or is this going to be a BCA table? All right. And that is important. You still have to do what we were doing in the previous video. You have to do a BCA to figure out how much was neutralized, and then an ice table to figure out the actual pH. Okay. So you're going to get into this routine when you have a neutralization going on of a BCA and then an ice. Okay. So yes, they are kind of long. Can't give you a ton of these on the test. Okay. But keep in mind, you just kind of have to watch what you're doing. Think about what you're doing. Do I need a BCA? Do I need an ice? Okay. It's a BCA if you have a neutralization going on. You have an ice if it is a weak something. All right. Okay. So the steps for these, like I said, step 1, you're going to do a BCA table. Why? What does that give you? That will give you your new concentrations of the buffer components. Buffer components. Okay. Now, if you still have some of each buffer, you can do an ice table. Ice will work, calculate how much H plus is in there, take the pH, or you can use the Henderson-Hasselbalch equation, which is a heck of a lot easier. So if you have stuff that has buffer components or a weak acid in its conjugate base, you can just plug it into the Henderson-Hasselbalch equation, and that will tell you your pH. So it does actually save a little bit of time. If you know you have a buffer, use the Henderson-Hasselbalch equation. All right, so we're going to do a couple examples of this. I'm going to have you try a couple examples of this. If you want to go ahead and start doing them, be like, I got this. That's fine. A lot of them are plug and chug, but watch your parentheses in your calculator. All right, so example number 17 says, in this problem, we will compare how the pH changes for water versus a buffer when adding either a strong acid or a strong base to each. Okay, so if I add a strong acid to water, it should drastically change the pH, make it way more acidic. If I add a strong acid to a buffer, the pH should not change much. Okay, so I've got 2 solutions here. It says, what is the starting pH of each solution? Well, let's look at these solutions. Solution A is 1 liter of pure water. Well, that's easy. The pH, I'm going to call it of A, is just 7, right? Pure water. Okay, so this is my solution A. Now the pH of B pH of B. How do I find that? Okay, what is B? B is a buffer made with 0.05 molar of acetic acid and 0.05 molar of sodium acetate. Okay, now this is a buffer. So this is my weak acid. This is its conjugate base. And the sodium doesn't do anything, right? You just can't add a negative ion by itself. So I can use the Henderson-Hasselbalch equation for this. Okay, so pH equals negative log of the Ka, which we've been using. You probably have it memorized by now. 1.8 times 10 to the negative fifth. Okay, plus, and I'm going to show you, if they're the same concentration, the log of 0.05 over 0.05, it's actually 0. So it's really just the negative log of the Ka. So we're going to get that the pH of this is 4.74. Okay, so yes, we do have different starting pHs, but we're going to show you what happens when I add an acid to each, how it drastically changes the water, but only barely changes the buffer. Okay, so what is the pH of each solution after adding 0.01 moles of hydrochloric acid, strong acid? Assume the volume remains 1 liter. Okay, because remember, if you change the volume, it changes the pH, so you would have to take that into account. So I'm not doing that in this. So say maybe I'm adding solid hydrochloric acid, which is impossible, but I'm adding acid in there and it's not affecting how much I have. Okay, so what is the pH after I add acid? So I'm going to do A first. Okay, well, I want to find the pH of, I added a strong acid to water. Okay, the pH is going to be the negative log of my H plus. That's it. Okay, now let's see, I had 0.010 moles of HCl. I have 1 liter to begin with. So that's pretty easy. The concentration of this is 0.010 moles over 1 liter, which is 0.01 molarity. Okay, so the pH of 0.01, or the negative log of 0.01, I get a pH of 2. So look at that. We went from 7 to 2 from adding 0.01 moles of hydrochloric acid. Now, what happens to the buffer? Okay, so first I gotta write what is happening, right? I'm adding hydrochloric acid, which really just means I'm adding H plus. Okay, so which part of the buffer is going to neutralize that? The acid part or the base part? Well, if I'm adding acid, then the base part is going to neutralize it, C2H3O2 minus. Okay, so what do you get when you put those together? Well, I get HC2H3O2. Okay, so I'm going to make a BCA for this reaction. It's always a BCA table first. How many moles do I start with each of these? Well, the H plus, I added 0.01 moles. C2H3O2, let's see. I had, 0.05 molar, 1 liter. That's 0.050 moles of this. I also have 0.050 moles of this. Okay, so I'm going to do minus x plus x, 0.010 minus x, 0.050 minus x, 0.050 plus. All right. Now, which one am I going to run out of? Well, that H plus is going to be neutralized. I have less of that. This one is 0, so x is 0.010. Plug that in here and plug it in here to see how many moles of each of these I have at the end. So this one, I have 0.040 moles of this left, and I have 0.060 moles of this. Okay, now instead of doing an ice table, now you can do an ice table, you're welcome to. But I know this is a buffer because I have a conjugate base and a weak acid at the end. I don't have any H plus, I just have this and this. I can do the Henderson-Hasselbalch equation. So pH is going to be a negative log of 1.8 times 10 to the negative fifth. We already know what that is. Plus the log of the A minus over the HA. So the conjugate base part, the base part is 0.040 over 0.060. Now, you might have noticed in the Henderson-Hasselbalch equation, both of those numbers are supposed to be concentrations, and I put in moles. Now, I did that because they are in the same solution, so they're both going to be in the same volume, so you can just use moles. It's fine. In this case, they're both in 1 liter, so this is also the concentration, 0.04 molar and 0.06 molar. Just kind of keep that in mind. You can use moles here. So what I get essentially is 4.57. All right, so look at that. That barely changed the pH. I went from 4.74 to 4.57 after I added that hydrochloric acid. So that is how that buffering works. Okay, so now I want you to try part C where I add the base. So instead of writing what happens when I add the acid, I would like you to try what happens when you add the base. So go ahead and pause here and give it a shot. Okay, so this was just going the opposite direction. Now again, pay attention to the OH minus in this part. So in A, I wanted to find the pH. Well, what I did is I found the concentration of OH minus, which was just 0.01. The OH is 2, so the pH is 12. Okay, so that drastically changed the pH in adding the acid. Okay. Now in solution B, I wrote what happened. So the hydroxide is actually neutralized by the acid part. So I have acid, weak acid, hydroxide. Well, those are going to, what's going to happen? The hydrogen is going to go from the acid to the OH minus. So I end up with conjugate base and water. Don't care about the water. I put in my starting moles of each. Okay, 0.05, 0.01, 0.05, -6, -6, +X. Okay, pulled those down. I run out of hydroxide here because it has a lower number. Plug in X, get the amount of weak acid and weak base that I have left. Plug those into Henderson-Hassbach and get 4.92. So again, the pH only changes just a little bit in the buffer. Now, if we did go past the buffering capacity, however, that would be a big change. All right, so what we're going to look at in number 18, I've got a buffer solution that's made by dissolving 0.016 molar or 16 millimoles, you can work in millimoles if you want to, of hydrofluoric acid, which was a weak acid, right? It's not one of our 6, and 0.008 moles or 8 millimoles of sodium fluoride, got its conjugate in it, right? In 100 milliliters of water. To it, 12 milliliters of 1 molar hydrochloric acid solution are added. What is A, the pH of the original buffer solution, and B, the pH after the hydrochloric acid is added? Now, if you want to pause this and go ahead and do it yourself, great, pause it now. I am going to walk through this though, all right? So part A, I want to know what is the pH of this buffer? Well, buffer, that word tells me I can use Henderson-Hassbach. Now, if I didn't actually say buffer, I should still know I can use it because I have a weak acid and I have its conjugate base. I have some F minus in there. So I'm going to write my Henderson-Hassbach equation. pH is pKa plus the log of A minus over HA. Awesome. Okay, so I'm going to plug all these in. Negative log of 3.5 times 10 to the negative 4th plus the log of, okay, which one goes on top? A minus goes on top, so that's NaF. So I have 0.0080 on top over 0.0160. You could have also done 8 over 16, get the same answer. But I would end up with is 3.15. Okay, so that's my starting pH of this buffer. Now, what happens when I add some acid to it? Okay, so we had to do BCA first. We got some neutralization going on, right? So I'm adding 12 milliliters of 1 molar hydrochloric acid. So I'm adding H plus. What is that going to react with? Well, it's going to react with the base part. So does it react with HF or F minus? Well, it's got to be F minus. If you make HF. Great, so I've got to be C, A. I am starting with C, 0.012 moles of this, 0.008 moles of this, and 0.016 moles of this. All right. Have A minus X plus X, 0.012 minus X, 0.008 minus X, 0.016 plus X. Now, I know this one's going to run out first. I'm just doing my BCA like normal. I know it's going to run out because it's less. So X is 0.008. Plug that in. I will have, let's see, 0.004 and 0.020. Now, I used all the F minus. That's what ran out. So actually, this solution went past the buffering capacity. I have excess H plus. Now, while you could do a weak acid, find the pH of it with that 0.020 hydrofluoric acid. Remember, if you have strong and weak together, the strong is what is going to completely dominate the pH. So I can just use this to find the pH, all right? So if I have 0.004 moles of H plus over, what is my total volume of solution here? So you had 100 milliliters and 12, so that's going to be 0.112 liters. Concentration there is, I don't know, I didn't write that number down. 0.004 over 0.112 is 0.0357, blah, 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 blah. Okay, so you do the negative log of that. I'm not rewriting that. Is 1.45. So you'll notice that pH actually dropped quite a bit, and that's because I went overing the buffering capacity. Okay, so I didn't use Henderson-Hasselbalch here, and I didn't use Henderson-Hasselbalch because I didn't have a buffer anymore. I used all of the F minus, so I can't use that. So I ended up with strong acid and weak acid. Strong acid dominates, just take the pH of that. Okay. Example number 19 is one you should try yourself. I'm going to read it and then tell you to pause. So what is the pH of a buffer made by adding 0.2 molars of NH3 and 0.1 molars of NH4Cl? So that's a weak base and it's conjugate base or conjugate acid. Okay, to 500 milliliters of solution. Kb for NH3, I gave you what is the pH after adding 15 milliliters of hydrochloric acid. Okay, so you can, if you want to look up the Kb equation, you can do that. What I would actually do is find the Ka, so 1 times 10 to the negative 14th over this Kb value, and still treat it as like, this is the acid part, and then this is the conjugate base part. That's what I would do. I would say weak acid, conjugate base. Or you can look up the equation for the Kb, whatever, either way is fine with me. So go ahead and give it a shot. Okay, so in the first part, like I said, I was just using the Ka equation. So I found the Ka first, which was 5.68 times 10 to the negative 10, plugged that in right here. And then I said, well, A minus is the base, so that's NH3, and HA is the acid, which is NH4 plus. So I plugged those numbers in here and got that my original pH is 9.55. Okay. And part 2, I added acid, right? I was adding HCl. And it would react with the base part. So I used NH3 to make NH4 plus. So I put in all my starting initial moles. So 0.015 moles of hydrochloric acid, 0.20 moles of ammonia, and 0.10 moles of ammonium. And minus X plus X, plug all that in. I know I'm going to run out of this one. Okay, so X was 0.015, plugged it back in. So I had some base and acid left, so I have the conjugates left, so I could plug that then into the Henderson-Hasselbalch right here and ended up with 9.45. So again, that adding of that acid actually doesn't change the pH that much. Now, if you got something drastically different, then it probably went over the buffering capacity, or you need to watch your moles and molarity and all of that. Okay. So application-wise, I mentioned this before, but there is a buffer in our blood. It's actually the carbonic acid buffer. So H2CO3 and HCO3 minus are carbonic acid and its conjugate base, and that's what actually buffers our blood. Okay, so we need, like I said, we need to be at 7.47. Oops, here, let me write. Is not allowing me to write. There we go. pH needs to be at about 7.4 plus or minus 0.05. That is not much leeway for our blood. Okay. Now the pKa of H2CO3 is actually 6.1. So remember I told you that it's best when pH equals pKa when you have the same amounts. Well, in our blood, we actually have to have different amounts of those in order to keep it at 7.4. So we actually have a little bit more base to make it at 7.4. So we have about 0.0012 molar of that weak acid and about 0.024 molar, about double of its conjugate base. And that is what keeps our blood at the correct pH. So this is actually kind of like the mechanism for it. I'm not going to go into this. But we use this is of course in hemoglobin. But what changes the pH actually is excess carbon dioxide, because that can affect the concentrations of carbonic acid in our buffer. So it is pretty complicated, but it is actually a really important process in our blood to keep that pH where it needs to be.